Okay, everyone, today's lesson starts on page 38, and it's on increasing and decreasing functions. So part A says, not all real-world situations can be modeled by a linear function. There are times when a nonlinear function is needed to describe the relationship between two types of quantities. So they're giving us different scenarios. They give us part A scenario, which is right here. Aleph is running at a constant rate on a flat paved road. The graph below represents the total distance he covers with respect to time. And also on page 38 in your book is Shannon's graph. She is running on a flat, rocky trail that eventually rises up a steep mountain. The graph below represents the total distance she covers with respect to time. So those two graphs are on page 38. Page 39 in your book starts to go over what I have at the bottom for, in your own words, describe what is happening as Aleph is running during the following intervals of time. So you might need to flip back between page 38 and 39 in order to answer this question. So if we look from 0 to 15 minutes on Aleph's graph, well, here's 0 time and here's 15 minutes of time. So I can see that he went a total of 2 miles. So he can run 2 miles in 15 minutes. Now if I do that again, so from 15 minutes, we're going to do right here, so from 15, whoops, I went up a little too far, whoops, so from 15 to 30, here's my increase now. We went from 2 to 4, so he can also run 2 miles in 15 minutes. And if we start to look at our totals, we have a total of 2 miles here, then plus another 2 miles would give us 4 mile total. Now let's look from 30 minutes, which is right here, to 45 minutes, which is right here. So he increased by, we started at 4 miles, and he increased to 6 miles. So once again, he runs 2 miles in 15 minutes. And if I tack another 2 miles onto my total, which remember is in the dark blue, after 45 minutes, he is at 6 miles. And lastly, from 45 minutes to 60 minutes, once again, he's increasing from 6 miles to 8 miles, so he's increasing 2 miles. So he can run 2 miles in the 15 minutes. And if I tack on another total of 2 miles, I'll get a total of 8. So after 60 minutes, Aleph is running 8 miles total. So 8 miles is his overall total. This graph in data is linear. Why is it linear, you may ask? Because it has a constant rate no matter what. Constant rate. No matter what, for every 2 mile increase, he is running 15 minutes. And also, whenever I graph it, as you can see here, I have a straight line, which also makes it linear. Straight line. So that's a good way to decide if something is linear or nonlinear. Always look at your graph. If it's a straight line, it is linear. No matter why all of these intervals match up in distance, because it's linear, no matter what, we're increasing 2 miles per 15 minutes. 2 miles every 15 minutes. So here's Shannon's graph, which is on page 38, and then the wording down here. We're going to check out those intervals as well. You're going to put those answers on page 39. So if we section off again, so from 0 minutes to 15 minutes, I would say we roughly gained 1.5 miles in that 15-minute interval. So from 15 minutes, which is here, to 30 minutes, which is there. So we went from roughly 1.5 to about, I'm going to estimate, to about 2.1, which is right there. So we had a 0.6 mile increase in 15 minutes. Now if I started at my 30 minutes to 45 minutes is right here, and I'm going to estimate here we have a rough 0.5 mile increase in 15 minutes. And I can see that because I went from about here, which it's hard to do on this graph, to about here. And I know my increments on my y-axis are going by 0.5s every time. And lastly, to stop it at 45 minutes, which is here, to 60 minutes, I'm going to say roughly I had a 0.4 mile increase. Now your answers could be a tad different depending on how you thought you were estimating each little area, but we should get fairly the same values. So after 15 minutes we were at, so I'm going to put my totals over here in dark blue, we were at 1.5 after the first 15. After 30 minutes I'm at a total of 2.1, and you could see that right here. I estimate that to be 2.1. After 45 minutes, I should be roughly at 2.6, which I am if I estimate that roughly at 2.6. And overall at 60 minutes, no matter what, if I add up all my data together, I should be at 3 miles. Now, just by looking at this graph, I see a curve. So since I see a curve, this is non-linear. It is definitely not a straight line, and there is no constant rate. No matter what, from each interval, we're not getting the same increase in mile every single time. So it's non-linear. There's not a constant rate, and you can also see from the graph we do not have a straight line, we have a curve. So here's just a little bit more of information to summarize. The rate of change of a function can provide useful information about the relationship between two quantities. A linear function has a constant rate of change, which means the same rate of change. So if it's linear, you're going to have the same rate of change, a constant rate. And if it's nonlinear, you are not going to have the same rate of change. There's not a constant rate. And remember, for linear, we always have a straight line graph. Straight line graph. They can be increasing or they can be decreasing. For nonlinear, as you can see here, I do not have a straight line. I have a curve or a decreasing curve. When you do nonlinear, you can still increase, you can still decrease, but remember, linear is always a straight line. Nonlinear, you always have a curve. And then remember, from a table to depict if something's linear or not, you can do the y minus y over x minus x. If you did that on this side, you would not get the same answer every single time. Going on to, this would be page 41 in your book. It says different breeds of dogs have different growth rates. A large breed dog typically experiences a rapid growth rate from birth to 6 months. So at that point, the growth rate begins to slow down until the dog reaches full growth around 2 years of age. They want us to sketch this data. So when the puppy is not born yet, the weight is going to be 0. So I'm going to say it's going to start to grow rapidly up until 6 months. So I'm going to draw like a pretty steep line here until 6 months. And then after the 6-month mark, it's going to start to like level off and just increase slightly. So roughly at age 24 months, I'm going to say this dog is about 60 pounds. But as you can see, since my graph was steepest here, it's growing the quickest, like the problem said, in the first 6 months. Is the function linear or nonlinear? So I'm going to say, and I hope you would too, that this is, that this is non-linear. I wrote NL for non-linear because the growth of the dog, the growth rate is not constant. Now, if it would have said in the problem that every month it was increasing by 2 pounds or every month it was increasing by 5 pounds, it would have been linear. But since it did not give us a specific amount per month, it is nonlinear. Like I said, right here, from 0 to 6 months, it's increasing in weight the fastest. Then it asks me if it's increasing or decreasing. Well, I'm hoping you're able to read the graph from left to right, and you can see that it's increasing, and it's increasing very quickly at the first 6 months, and then steadily increasing not so fast for the rest of the 2-year period. And it's increasing because my line is going up. Number 4 is on page 42 in your book. Nika took her laptop to school and drained the battery while typing a research paper, which sometimes that happens to you all, especially with your iPads. When she returned home, Nika connected her laptop to a power source, and the battery recharged at a constant rate. Bingo! It said the word constant rate. They want us to sketch the graph. So my axes are labeled time in hours and battery charge for 100%. So I'm starting at a 0 battery charge because it was drained, it said while writing the research paper. And then it was recharging at a constant rate. If we just have to sketch it and it's increasing because it's recharging at a constant rate, I'm just going to draw a line that is increasing, and it is linear because of that key buzzword right there, constant rate. And when we graph something that's linear, remember, you know that it is a straight line. Is the function represented by a graph that's increasing or decreasing? And in this case, I'm hoping you would be able to say that it's increasing because the battery is recharging. And if you look at the graph from left to right, you can see that my line is going up. Now for number 5, it says the long jump is a track and field event where an athlete attempts to leap as far as possible from a given point. Mike Powell of the U.S. set the long jump record of 8.95 meters or 29.4 feet during the 1991 World Championship in Tokyo, Japan. They want us to sketch a graph. So since this long jump might be a little more difficult for some of you to visualize just by me talking about it, I'm going to provide some data points and I want you to plot them. So over here I put down the table of values that I would like you to attempt to plot and estimate on the graph provided right here, and then I want you to answer B and C. So try to do this, and you can pause the video when you have this page complete, press play, and check to see if you have the correct answers. So if you plotted this data correctly, you should see something that looks like this. I didn't connect my points just because I wanted you to see roughly where my data would be, but if I did, I would sort of have a graph that looks like that. I'm hoping you said that it was non-linear, that's why I wrote NL, because the rate of change is not constant, and when I looked at my graph, I had a curve instead of a straight line. Also, the function, is it increasing or decreasing? Well, in this case, both are occurring. It's increasing from the beginning of the jump to when they reach the max height, and then once the person reaches the max height, they have to start to descend to get back to the ground, and that's whenever it's decreasing. So it's basically increasing over here until it reaches the max height, and then descends once they reach the max height. So this is a Ferris wheel problem. I know a lot of you like to ride on a Ferris wheel at a carnival. And it says Lamar and his sister are riding a Ferris wheel at a state fair. Using their watches, they find that it takes 8 seconds for the Ferris wheel to make a complete revolution. The graph below represents Lamar and his sister's distance above the ground with respect to time. I want you to try to answer questions 6 through 9 on pages 44 and 45. And when you are ready to check your answers, you can press play. So please pause the video right now, try to do it on your own, and then you can press play and check your answers. So for 6A, I'm hoping you said that it was nonlinear because it's not a constant rate of change, and this graph is definitely not a straight line. It's going up and down, up and down, up and down, and so forth. When is the function increasing? Now your estimates could be a slight different than mine, but it should be in the same ballpark figure. So I'm increasing from 0 to roughly 4, from 8 to 12, 16 through 20, 24 through 28, and roughly 32 through 36 time intervals. And it's increasing because when you're riding the Ferris wheel, you would be rising in the air at that time. The next question asks, when is it decreasing? Well, that's whenever the graph's starting to go down. So I would say from 4 to 8, 12 to 16, 20 to 24, 28 to 32, and 36 to 40. And at that time, when you're on the Ferris wheel, it's traveling back down to the ground. So remember, you go up, 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 up as high as you can, and then once it reaches its max height, you're going back down to the ground. So here's the same question, which is on page 45. Questions are 7 through 9. If you have not already completed these, do so now. Press pause, and then when you're ready to check, you may press play. So how high above the ground is the platform for the passengers to get on? Well, here's where the graph starts at, and that's at 5 feet. That's the lowest point on the graph. So that's how far above the ground the platform has to be for the passengers to get on. Number 8 says, how many revolutions would the Ferris wheel go in 40 seconds? Well, there's going to be a total of 5, because if we start here, we have 1, then we have 2, we have 3, we have 4, and we have 5 revolutions. Because remember, for a full revolution, it has to go up to the very top and then back down to the ground. What is the diameter of the Ferris wheel? This could have been a tricky question for you, but remember, all you have to do is take your highest distance above the ground minus your lowest distance above the ground. So by looking at the graph, I saw that my highest point, no matter what, was at 45 feet. My lowest point was where the platform for the passengers were, and that was 5 feet, and if I subtract them, that's a 40-foot difference. So the whole diameter of the Ferris wheel from the lowest point, which was at 5 feet, to the highest point, which was at 45 feet, the difference there was 40 feet. I hope this information helps you understand linear and nonlinear, increasing and decreasing functions a bit more. Make sure to star anything that you did not understand, and you can ask your teacher. Thank you.